Okay, good afternoon. Do you have any questions for me? No questions? Okay. The experiment, it doesn't, if you look at the lab manual, it doesn't have a lot of information about the SN2 and SN1 reactions. Just want to make sure that is the lab manual shared or no? Can you see it or no? No? Okay, so it should be now. Okay, so it's the first part of this experiment is preparation of alkyl halide from alcohol. The reaction or the type of reaction or the mechanism that is used for that is a substitution reaction. And specifically, this is a SN1 reaction. SN1 stands for nucleophilic substitution. That's for SNN. And then 1 means is unimolecular. What does it mean? It means that in the rate determining step, I'm going to add more theory to this experiment for the new edition, because I was reading and I say, like, if the lecture has covered it already, you should be fine. If the lecture has not covered, then it's not, the lab manual is not enough unless you read this from the lecture. So I will add more theory to it for the next edition. So for the 1, meaning unimolecular, that means the rate determining step is the, yes, I have to do the rate determining step and all that in the lab manual. So the rate determining step is the slowest step of the reaction. So SN1 is a 2-step reaction. First, carbocation forms, and then the nucleophile forms bond with the carbocation, and you have the final product. The second part, where nucleophile forms bond with the carbocation, that's fast step because carbocation is very reactive, so the reaction happens very quickly. But for the first part, where you have the alcohol, when OH leaves and forms the carbocation, that is the slow step of of these 2 steps. Slow step is rate determining step. And in the slow step of reaction, there is no chloride. So that means the rate of this reaction is going to depend on concentration of the alcohol only. So this is called SN1 reaction. One compound is to concentration of only one of the reactant is affecting the rate of this reaction. So the rate depends on concentration of the reactant. In this specific reaction, OH is not a good leaving group, and because it's not a good leaving group, then we have to protonate first. So we protonate it to change it to H2O. So we have a H2O or OH2. That is, H2O is a good leaving group, so would leave, and the carbocation forms. So we have to use the catalyst. That's what the HCl is used for here. HCl, it provides the proton to protonate the OH to change to better leaving group, and it also provides the Cl-, which is the nucleophile that comes in second step. Okay, and for part A, so we are going to for part 1. For part 1 is the synthesis. Part 2 is the comparison of the reactions. So in part 2 of the reactions, we are going to look for comparison. So in bimolecular nucleophilic, the nucleophile comes in the same step, the leaving group is going to leave. So concentration of nucleophile and substrate, so the alkyl halide is known as a substrate. Concentration of the nucleophile and substrate both are involved in the rate determining step. So there's just one step. That's why it's called bimolecular nucleophilic substitution. It's one step. In unimolecular, you have 2 steps. You have slow step and and then you have the fast step. Only slow step is going to determine the rate of the reaction. The second part of this experiment, in part 2, we are going to compare to see how structure of alkyl halide is going to affect the substitution reaction, reactivity of alkyl halides. Now, if the reaction is SN1 reaction, carbocation has to form first. Facts to know: if the intermediate, which in this case is carbocation, is more stable, then it's going to form faster. So if the tertiary alkyl halide goes through SN1 reaction, first tertiary carbocation is going to form. So when tertiary carbocation forms, this is more stable, then you are going to get a faster reaction. So tertiary carbocation is more reactive toward SN1 substitution. On the other hand, when it's a SN2 type reaction, in SN2 type reaction, because both of them is going to take, both action is going to take place in one step, the less hindered the alkyl group is, or the alkyl halide is, the faster the reaction. Because if you have a tertiary alkyl halide for SN2, nucleophile has to come in and attack a tertiary carbon, and is going to be hindered sterically because you have too many groups around it, and it's going to make the reaction slow. So if you have a primary alkyl halide for SN2, is going to go fast. So we have fast step or faster reaction. If you have primary alkyl halide, is going to be a slow reaction if you have tertiary. Tertiary alkyl halide doesn't go through SN2 reactions because of steric hindrance. Primary is the fastest one for the alkyl, for the SN2 reaction. So this is something that you also learn in lecture, but what we are going to do in the lab today is to experiment it and find, based on the evidence of the reaction, to see which one is going to go faster. Yes, methyl would be faster. Perfect, Sammy. Methyl halide is going to be faster for SN2 reaction compared to primary even. So for the part 1 of the experiment, which is synthesis, you are going to use the volume of the or the mass, whichever is given, based on the procedure, and then you calculate the theoretical yield. You find the final the mass of the product, and then you can calculate the percent yield, just like how you've been doing it so far. You have to prepare and find the percent yield for part 1. For part 2, you have A and B. For A, which is the SN1 reaction, you are going to compare these 6 compounds, or as many as you see in the video, and say which one is going to go faster for SN1. Now, if it's SN1 and carbocation forms, tertiary is going to be faster, right? So 3 would be faster than 1 for SN1. How do we know it's SN1? Condition of the reaction. Like if you use silver nitrate, aqueous solvent, that is SN1 condition. Any polar protic is going to promote SN1 condition. Silver is going to stabilize the carbocation and is going to promote, again, SN1 reactions. Now the other factor is the leaving group. So between 1 and 3, which one would go faster for SN1? Yes, polar protic solvent is good. It would be good for SN1. T-butyl would be faster for SN1. Very good, very good. And between 1 and 4, which one would be faster for SN1? 1 and 4? 4 because it's bromo, and bromine is a better leaving group. So bromine is better leaving group than chlorine. That's why 4 would be better. But a good leaving group is going to be good and benefit for both SN1 and SN2. So either one, in either case, you have the advantage. But substrate 1 is primary carbocation, is not stable, so it doesn't form. But for the 3, the tertiary is going to form better. So there are two factors. Silver nitrate. So when you have silver nitrate, is it's going to give like lots of ions, and that ions that you have, like when carbocation forms of the plus charge, you have the nitrate next to it, is going to stabilize carbocation. So when you add silver nitrate, you expect that reaction go through SN1 reaction or formation of carbocation. It's going to just make the condition of the reaction more suitable for formation of carbocation. Good. So, and then as you use the same chemicals, but using aprotic solvent, no silver nitrate, that would be SN2 condition. For SN2, which one would be faster, 1 or 3? For SN2, 1 would be faster, very good, because 1 is less hindered and is more available for nucleophile to come in. And for SN2, the less hindered the substrate is, the faster the reaction is going to be. And between 1 and 4, which one would be better for SN2? 1 and 4? I think it's 4. The reason is 4 because good leaving group is good for anything, right? In terms of the steric hindrance, yes, you have primary, both of them are primary, but since the BR is leaving and the attack is from the opposite side, is not going to affect that much. I see what you're saying, Craig. So you do have larger size of BR, but since it's leaving and the attack is from the opposite side for SN2, so BR is not, the size of BR is not going to hinder. It's more of a primary, secondary, or tertiary. AgNO3 is not protic. But when you have AgNO3 solution, it's in the water. So the OH from the water, it's going to make it protic solution. So AgNO3 is not the protic solvent. The AgNO3, if it was solid compound, is not protic. But since it's an aqueous solution of AgNO3, the water is making the protic definition of the protic. Right, Sammy? Does it make sense? No. So yeah, good. So that's all you're doing today. Just so you can do two things. Actually, since you are not in the lab, you have to watch the video to see what has been done. I don't remember, and even if I remember, I don't want to tell you how you are either counting the time or just relative. Which one? How long does it take for the precipitate to form? Evidence for reaction is formation of precipitate, and I only monitor for 20 minutes, no more than that. Actually, 5 minutes would have been good. Like for tertiary, it's for SN1, the precipitation is right away less than 1 minute. For secondary, would be like between 1 minute and 5 minutes, or less than 20 minutes is going to form. And if it's primary, it's not going to form precipitate within the 20 minutes, and then you would just say no reaction at room temperature. Okay, because the temperature can affect, but we are not studying the temperature, effect of temperature. We are just studying the nature of the substrate or reactivity of the alkyl halide, and the comparison is like at room temperature, all of them at room temperature. That's what we do, just the room temperature. Yes. Any questions for me? Any questions? Okay, if you don't have questions, I'm going to call for attendance, and I want you to give me the time that the review is included. I think it's either experiment 9 or 10, so I can, now that I'm using YouTube, I can cut that piece and post it separately as just a review for the exam. I know it's part of the lab though, the experiment 10 most likely. Just give me the time, any of you, if you volunteer, please. When you watch it, tell me what is the time frame for the review, so I can take that chunk out and put it separate file for just the review for the exam. But you do have the review for exam already recorded. And if you have any questions, I will. Perfect. Thank you. Thank you so much. Is it? Okay, perfect. It will be on YouTube from now on anyway. That's good. That's good. Some multiple choice, but not all multiple choice. And we talk about more next week with that. After you watch the video, if you have any questions, you would tell me. Sure. Deja? Sure. Okay. Tarek? This is for attendance. Ashana? Elizabeth? Jennifer? Alexis? Kylie? Valentina? Maria or Mariah? Mariah? Catania? Okay, you got the videos in time, right? You don't need me to extend the date, but the date for lab report is you could submit it late. I won't take points off for if you submit it until like tomorrow noon sometime, just because the videos were out for like day or so. Catania, are you here? No? Okay. And Mariah? Okay. And then? Sammy? Cassandra? Craig? Antonia? Okay. I will make this video, today's recording, public, so you can see it. You could, anything that we record this semester, you have access to it. So I'm going to make it public so you can watch it in case if you need to watch it again, or anybody who missed the class today can watch it. Questions for me? Some of you had questions about the percent yield for the last experiment. The percent yield of 51.8, it's okay. The problem is that product was very volatile, and it could have, evaporate or not condense properly, and you can include that in your. I'm sorry, I didn't respond to that email. I got the email from a couple of you. I don't know if I responded or not, but I just want to make sure that if you have submitted yes, it could be. Could be like, it's vapor, and it's very volatile. So the normally is that apparatus is open, there is a leak, but for this experiment specifically, you could say condensation also was not efficient. Okay, I'm going to stop recording